energy. So we're talking about corrections, first order correction to the eigenenergy, right? E1 or En1. Okay. Now from chapter 4, that's what it was. Okay, quite a while back. We found solutions to the eigenfunctions for the simple harmonic oscillator, the SHO, and they're of this form. So if you've forgotten, go back to chapter 4, revise, and these are the eigenstates for the simple harmonic oscillator that is unperturbed. It was only the simple harmonic oscillator. And look, it's an exact term, it's not a numerical approximation with real numbers. It's in a nice, simple, exact form. So, alright, so now we're asked to find the first order correction to the eigenenergies. In other words, we're asked to find En1. Now remember the formula here. So En1 is just the diagonal term, Nn, of the perturbing matrix, which is just the expectation value of the perturbing Hamiltonian, which is H hat dashed, which in fact is just alpha x to the fourth. You just plug that in here, right? And we know the U naughts, that's just this, so we just plug this into here and here. Now this is a real number, so conjugating it won't have any effect, right? So effectively we're just squaring this and putting this in here, which is alpha x to the fourth. So this then becomes, now alpha is just a constant, right? So it can come outside the integral. Where does this come from? Well, if you square this, you'll get the square root of that. That's what this is, right? Just a constant, comes outside the integral. You've got an x to the fourth from here, that's your h dashed, the alpha's out here. And you square this, because you've got this here and here. So the 2 here will disappear, so you're just left with my m omega x squared over h, and the 2 disappears because you've squared it, you got it twice, right? And you can look at, let me just check, I should have checked this. There's a table of integrals in one of the appendices in the textbook. Appendix. Was it D? Let me just check. E. Appendix E. Here, I'll just sort of get close to this. Useful integrals. So x to the fourth, e to the constant x squared. Is there something like that in the text? Yes, there is. In the text, it's the integral of x to the power 2n e to minus a squared x squared. Well, you can easily adjust that. Okay, so you can find this yourself. You could do that for homework by consulting the useful integrals, Appendix E, in the textbook. All right, and the final result is this. Okay, so that will be your change, your correction. It'll be your delta E, your first order correction to the energy eigenvalues. Right? So now it's the ground state, so your n is 0. Right? The ground state just means the lowest energy level in your simple harmonic oscillator, SHO. Okay? So the ground state wave function, which is this, U naught. So this is the correction to the energy, the lowest energy, due to this perturbing term. Okay? Alright, second example. Now, I just have enough, before running out of board, just enough lines to introduce to you what the problem is, what the application is, and to explain to you what the perturbing Hamiltonian is, H dashed. Okay? So, well, just from the title, so you're polarizing a hydrogen atom. What does that mean? Well, you put the hydrogen atom in an electric field, let's say a strong electric field. Now if you polarize it, that means, what will that mean? So if the electric field, let's say, is directed this way, vertically along the z-axis, then and imagine my fist now is the hydrogen atom. Well, how can you get an electric field? Well, say you have two plates attached to a battery, and let's see. So this is your positive plate, this is your negative plate. So there are more electrons here and less electrons here. So the electric field goes from, well, it's only a convention. I'm forgetting my electromagnetism. Anyway, you've got an electric field directed one way or the other. And so the, let's say the positive plate's here, so the negative charges of the whole atom. Now the atom's normally neutral, right? But it has spinning electrons, they're negative. So if the positive plate is sort of like here, then the electrons will probably spend more time at this end of the atom, and so the atom becomes polarized. So sort of like this region here becomes more negative, and here's the negative plate creating the electric field. So this part, this pole, if you like, North Pole, South Pole, will become more positive, right? So you've now got a distribution of charge over your atom, so it is polarized. It's two charged poles in a sense. Okay, so so you're polarizing the hydrogen atom. Okay, and now you're assuming the H atom, the hydrogen atom, is in its ground state. And you're asked to find the energy shift, in other words, the energy corrections, the E1 to second order, and E2, right? So you need to find. Now we've done formula for both, for E1 and E2. E2 formula was in the previous session. So you apply those two formula when your H bar is this. This is, now where's this come from? Well, little e, that's the charge in the electron. We're talking about the hydrogen atom, right? And big E, that's your electric field strength. So the force felt by the atom, is that correct? Will be the charge, the force on a charge in electric field E is QE, where Q's the charge. So this presumably is like the force on the what? The atom, I guess. And Z is just distance. Now, force by distance is work by definition. You apply a force over a given distance, Fx, Fd, distance. That's the work done. So that's potential energy. And, if you do, like 1 volt, how do you define that? Well, it's the work done moving a charge through the potential energy of 1 volt. Does that make sense? That's circular. I need to think. It's been a while. The definition of a volt is defined in terms of work done by moving a charge over a potential difference. Yeah, well, anyway. So force, distance, that gives you work, which is potential energy, and that's the perturbing term, H dashed, right? So it's minus E to make this positive, because the charge in the electron is negative. So minus E, big E, the electric field strength, Z. So that is your perturbing H bar. So we will plug this formula into the perturbation matrix, the MN matrix from session or two back, okay? And we'll use this formula to calculate the first and second order corrections to the eigenenergies, right? But I've run out of boards, so till next time.